Okay, now let's talk about our second solution. This solution is due to Richards-Stanley. The idea is as follows. So look at this inequality. This is the same as saying a minus ab is a non-negative number. So this is what we want to prove. Now recall in linear algebra, what kind of quantity, what kind of number is non-negative related to a matrix? In linear algebra, the eigenvalues of a positive semi-definite matrix are always non-negative. We will abbreviate this as PSD. And now the goal is to find a PSD matrix from this matrix H with n minus AB as an eigenvalue. So that is the idea of the proof. To do this, first we observe that without loss of generality, we may assume remember, by hypothesis, H has an A by B submatrix whose entries are all equal to 1. So without loss of generality, we may assume that the A by B submatrix of all ones occupies the first A rows and B columns. The first A rows and B columns. Otherwise, we'll just permute the rows. That doesn't affect the fact that H has rows mutually orthogonal. Okay. Now let M be the submatrix occupying the first A rows and the last n minus B columns. Now, to make it easier for you to understand, let me draw this matrix. So this is the matrix H, which is n by n. Now we have moved all of the entries in this A by B submatrix to the top left corner. So this is that A by B submatrix. And M is here. M has A rows, but the minus B columns. Now let us look at the matrix M times M transpose. Which is an A by A matrix. And it is clear that this matrix, its product, is PSD, positive semi-definite. It turns out that this matrix MMT can be specifically computed. Specifically, MMT is equal to the matrix has n minus b's on its main diagonal, and all the other entries are all equal to negative b. To verify this claim, let us give entries in H the notations. We use HIJs to denote the entries in H. Under this notation, this matrix M is. Now with such notations, it will be easier for us to compute MMT. The ijth entry in the matrix MMT can be computed through taking the inner product of the ith row and jth row of M. Noticing that here we are taking the product of M and its transpose. So this is literally just the jth column of the transpose of M. To compute this inner product, we'll take advantage of the orthogonality between rows in H. We'll write this as the difference between the inner products of the ith row and jth rows of H minus the inner product are we truncated at the first B columns. Now this part is equal to zero if I is not equal to J, because of the orthogonality of the rows of H, and it is equal to n when I is equal to J, because when I is equal to J, they are identical, and each entry of H, remember by assumption, is plus minus 1. So we are just summing up the squares of plus minus 1s. So we will get n. And this guy is always B, because we are taking entries from here. They're all 1s. So this is just a 1, 1, 1, 1 dot product with 1, 1, 1, just B. So in the end, we're going to get n minus B if I is equal to J, and negative B if I is not equal to J. This verifies our claim. So now we can finish the proof. It follows that MMT has the column vector with all 1s as its entries as an eigenvector with eigenvalue n minus AB. So this is very easy for us to verify, because if you multiply this with this vector, you'll find you're summing up a many negative bits plus n. This matrix is a by a, so there are a many negative bits and n. So n minus ab is non-negative as an eigenvalue of the PSD matrix MMT. And we are done with the proof.